Today we are going to discuss periodic table. So in periodic table topic, we will discuss general introduction to periodic table, followed by chemical periodicity of the physical properties of the element. After completing the periodic table, students should be able to use the periodic table more effectively, discuss chemical periodicity of the following physical properties, which are atomic radii, ionic radii, ionization energy, electron affinity, as well as electronegativity. And students should be able to explain the effect of effective nuclear charge and shielding on the chemical periodicity. In periodic table, it can be described according to periods. Okay. In periodic table, there are 7 periods, period 1 until period 7. So short period, for example, period 1, only with 2 elements, hydrogen and helium. Period 2 from lithium to neon, and period 3 from sodium to argon. And we also have long periods involving d and f orbital. You can notice that the period number 1 until 7 is determined by the outermost shell. Periodic table can also be described or be explained according to blocks. Periodic table can be divided into 4 parts based on outer electron configurations. For example, S block elements, which is the main group on the left, we have group 1 with outer electron 1 and with outermost electron 1, and group 2 with outermost electron 2. And we have P block elements starting from group 13 to 18 at the right side of the periodic table. We have D block elements starting from group 2 until 12, followed by F block elements, lanthanides and actinides. Each block can be further divided into columns. This structure of periodic table can be used to predict the filling order of the orbitals when writing electron configuration. Look at representative elements. Representative elements consist of S block and P block. Periodic table also have D transition elements. It's in the middle of the periodic table. The characteristic of D transition elements, 1, D transition elements is characterized or has specific properties due to each element in transition element has D electrons. The main characteristic due to D electrons that all the elements in the transition element exhibit smaller variations from row to row compared to representative elements. Next is F transition metals. Electrons are being added to F orbitals. Consequently, very slight variations of properties from one element to another element. This is the structure of periodic table. You can see blue here represent the representative element. The pink group here is also a representative element. The D block here is transition, D transition element, whereas the gray here is F block element. The first physical properties that we will discuss is atomic radii. There are three types of atomic radii: covalent radius, metallic radius, as well as van der Waals radius. Before we can discuss the chemical periodicity of the physical properties, we have to discuss the meaning of effective nuclear charge. Effective nuclear charge is the amount of positive charge felt by the outer electron in atoms due to the attraction from the nucleus. The effective nuclear charge felt by the outer electron is determined by the difference between the charge on the nucleus, here means 3+, and the charge on the core, means the inner electron. It is definitely lower than the atomic number because of shielding by the inner core electron. There are a few points to remember about shielding effect. One is electrons on the right side of the NS and NP does not contribute anything to effect of shielding. Means that if the electron is here and you have more NS and NP outside to the right of the electron, it will not contribute to the shielding effect. Electrons in the same group, NS and NP, will shield with value of 0.35 respectively. Means that if you have another electron here or in the same N, okay, it will only contribute the shielding effect towards this particular electron with the value of 0.35. Number 3, electrons in n equal to 1 orbital will shield with value of 0.85 respectively. Means that if this electron, okay, the n minus 1 compared to the original n of where this particular electron is located, will contribute a shielding effect of 0.85. Any electrons in N further downwards, for example here, the shielding effect towards this electron if the first orbital below the electron that we are talking about, the value of the shielding is 0.85. And if we go further down of the orbital n-2, then the value of the shielding effect now is 1. So there are three values that can be considered with shielding effect. One, electrons in the same group, regardless s or p orbital, will give the value of 0.35. The second one, electrons in n-1 for the compared relative to the orbital of the electron that is in question, will shield with the value of 0.85, and electrons in the n-2 compared to relative to the orbital of the electron that is in question will shield with the value of 1. If the electron shielded is in ND or NF, then rules 3 and 4 will be all electrons on the left side of the groups will shield with value of 1. So with the effect of shielding means that the attractive or the attraction from the nucleus is less due to the shielding effect of the inner electron. If we look at the trend in the periodic table, atomic and ionic sizes increases with increasing n. Means that increasing n is from top to bottom. This is due to n, the number of n is getting larger from top to bottom in the group. Whereas going across the period, which is from the left to the right side, the size is getting smaller due to increase of effective nuclear charge. And why is the nuclear charge, effective nuclear charge increases? Because from left to right, the atomic number, which determine the positive charge attraction, increases from left to right. From top to bottom, due to the number of n getting larger from top to bottom, definitely the effective nuclear charge decreases from top to bottom because of the position of the electron is far away from top to bottom with relative to the nucleus. What about ionic radii? If you look at this table, for example, lithium and beryllium, the atomic radius for lithium is 1.52, but when it becomes ion, lithium plus means that it has released or lost one electron. The ionic radius is 0.9. And look at the second one, beryllium. Atomic radius originally is 1.12, and when it is ionized into beryllium 2 plus means that it has lost 2 electrons, then the ionic radius is now 0.59. So this is due to the contraction, means that when this lithium and beryllium lost electrons, the contraction or the effective nuclear charge becomes much more significant, thus the radius of the ions is much smaller. Look at the table. You can see from here more examples: sodium, magnesium, aluminium. And based on the charges, if it is more positive in charge, means that the element has lost more electrons, then we can see the ionic radius is much more smaller. In general, cations are always smaller than their respective neutral atoms. Anions are always larger than their neutral atoms. This is the example of anions. You can see here we have nitrogen, oxygen, and fluorine. The neutral atoms, the atomic radius of nitrogen is 0.75, oxygen 0.73, and fluorine 0.72. If we look at the anion, nitrogen 3 minus means that the nitrogen now has an additional 3 electrons. The ionic radius now becomes 1.71. And oxygen O2 minus with the additional of 2 electrons, the ionic radius now is 1.26. Whereas for fluorine, with additional of 1 electron forming fluoride, the ionic radius becomes 1.19. With regards to anions, increasing electron numbers in highly charged ion cause the electrons to repel, thus increase the ionic radius. The second physical property that we will discuss is ionization energy. Ionization energy is the energy required to remove an electron from an isolated gaseous atom. First, ionization energy means that energy involved in removal of the first electron. Second, ionization energy means that the energy required to remove the second electron. The trends in ionization energy, or simply known IE, are the opposite of the trends in atomic size. In general, larger atoms have lower ionization energies. Look at the trend, let's say according to the groups. From top to bottom, the ionization decreased. This is due to the larger number of N when it goes down from top to bottom. When the N is getting larger, the electron is much farther from the nucleus, which results in less effective nuclear charge. And that is why the ionization energy is decreasing from top to bottom in a group. Let's say if we discuss from left to right, according to the period. So from left to right, we already discussed just now that the effective nuclear charge is getting larger. So if the effective nuclear charge is getting larger, means the attraction from the nucleus is much more effective towards the electron in the outermost layer. So it is much difficult to remove the electron, means that the ionization energy is higher. So when we move from left to right in the periodic table, the effective nuclear charge is increasing. The ionization energy also increase, means that it is more difficult to remove the electron. Higher energy is needed. With regards to ionization energy for the second electron or second ionization energy, the value of second ionization energy is always much higher than the value of ionization of the first electron. If we look at this graph represents the period. For example, period 1, n equal to 1, period n equal to 2, period n equal to 3, and so on. So you can see here from left to the right, the ionization, the first ionization energy is increasing. Same goes to the n equal to 2, the ionization energy increases towards to the right, n equal to 3 as well. But there is a bit of variation which we'll discuss later. For example, if we look at beryllium and boron, there is a slight difference, okay, where boron is supposed to have higher energy compared to higher ionization energy compared to beryllium, according to the trend from left to right. But there is a slight difference, which is ionization energy for boron is a bit lower compared to beryllium. We will discuss this in class. There's another variation, which is nitrogen and oxygen, which is, according to the trend, oxygen ionization energy should be higher than nitrogen. But the actual ionization energy is a bit lower for oxygen compared to nitrogen. We can see that the deviation happens to boron, aluminium, and gallium in group 13. Let's look at the table for group 1, group 2, group 3, group 13, and group 14. Group 1, the first ionization energy is 496, and the second ionization energy is much higher, which is 4,562 compared to the first ionization energy. This is because Removing one electron from group 1 is much easier because the electron in the outermost orbital or valence electron for group 1 is 1. In order to remove the second electron, okay, the electron has to be removed from the inner orbital, which is much more difficult. Now, of course, the ionization energy for the third electron and for the fourth electron is much more higher. Now, if we look at group 2, for example, magnesium, the first ionization energy is 738. The second ionization energy is 1451, but the third ionization energy is 7733. So we can see a big difference in terms of value of between the ionization, the second ionization energy with the third ionization energy for group 2. This is because the valence electron for group 2 is 2 electrons. So for the third ionization energy, which is to remove the third electron, the electron must come from the inner orbital. If we look at group 3, since there are 3 valence electron, so you can see the fourth electron, which is the ionization energy, the fourth ionization energy, the energy is much, much higher compared to the third one. So from this trend, we can identify, from the trend of the ionization energy, we can identify the group of the element. The reason for sodium forms Na plus and not Na2 plus is that the energy difference between IE1 and IE2 is so large. The same trend is persistent throughout the series. Okay.